On January 1st, the latest images of the interstellar object 3 Atlas were leaked, and these may be materials that NASA has not yet disclosed. This data was quickly confirmed by multiple independent observatories, including amateur astronomers, thereby ruling out the possibility that the observed phenomenon was caused by equipment malfunction or image processing techniques. What is particularly noteworthy is that 3I Atlas continues to maintain a stable level of activity and a clearly organised structure even though the object has already passed perihelion and is moving away from the primary heat source of the solar system. This behaviour does not align with the typical post-perihelion decline model of comets, which usually exhibit rapid fragmentation and a loss of structural organisation. The existing observational evidence suggests the possible presence of an internal energy source or a non-traditional emission mechanism that does not rely entirely on solar radiation. Although a final conclusion cannot yet be drawn, the current data is sufficient to raise serious questions about the limits of conventional physical models. The encounter with Jupiter, scheduled for March 2026, is considered a decisive test. In the next section, we will evaluate the trajectory of 3I Atlas, as this new development will be closely compared with predictions based solely on gravitational dynamics in order to determine whether the object's motion fully follows natural laws or shows signs of anomalous adjustments. The image set released to the scientific community consisted of 2 parallel representations, one composed of raw frames and the other produced through contour enhancement, and both were derived from the same observational sessions aimed at 3I Atlas. 3I Atlas was therefore not being viewed through a single interpretive lens, but through 2 complementary treatments of identical photon data, one preserving the unaltered signal and the other revealing subtle gradients embedded within it. In the raw frames, the coma of 3 Atlas appeared faint and restrained as expected for an object at this distance from the Sun, yet careful inspection revealed a non-uniform distribution of brightness that subtly favoured one direction. 3. Atlas did not display a chaotic or noisy field in these unprocessed images, but instead presented a soft asymmetry whose geometry remained consistent across successive exposures. The contour-enhanced images did not invent this asymmetry, but traced it, converting small variations in intensity into visible lines that mapped the underlying structure of light surrounding 3 Atlas. 3 Atlas therefore revealed the same geometry in both representations, one subdued and one clarified, creating a rare alignment between raw observation and mathematical emphasis. If the structure associated with 3 Atlas had been an artifact of processing, it would have emerged only after enhancement and would not have been detectable in the unprocessed frames. 3I Atlas instead showed congruence between both image types, with orientation scale and direction preserved regardless of visualization method. This alignment established a critical anomaly because the structure extended sunward rather than trailing away from solar radiation, and such orientation runs counter to the dominant forces that typically shape cometary comae. 3I Atlas therefore occupied a narrow conceptual space where the data was neither dramatic nor dismissible, existing instead as a persistent deviation that resisted easy classification. The significance of this moment did not lie in the sharpness of the feature alone, but in the fact that 3I Atlas maintained coherence between observational layers that are often at odds in ambiguous detections. 3I Atlas invited scrutiny rather than speculation, because the images did not shout contradiction but quietly declined to conform. This initial verification phase did not seek to explain the behaviour of 3 Atlas, but only to establish that something measurable was present, something rooted in the distribution of light itself. 3. Atlas thus moved from being a transient point of interest to becoming a subject of sustained examination, as the images formed a stable foundation upon which deeper questions could rest. With the physical reality of the structure now anchored in consistent observation, attention naturally began to drift toward a more demanding inquiry, one that would ask not what was seen around 3 Atlas, but why such order persisted where decay was expected. Contour enhancement is often misunderstood as a process that adds information, yet in reality it performs a far more restrained operation, one that simply reorganizes what already exists within the data recorded from Atlas. When light from Atlas reaches a detector, it arrives not as a clear shape, but as a field of subtle intensity variations, and those variations remain largely invisible to the human eye when viewed in raw form. The contour enhancement process does not alter the photons collected from Atlas, but instead calculates the gradients between neighbouring brightness values, allowing regions of slow change and rapid transition to be distinguished. In this sense, contour enhancement behaves like a translator, rather than a creator converting numerical differences into visual boundaries that reflect the original light distribution around Atlas. If the coma of Atlas were truly uniform, contour enhancement would reveal little more than concentric symmetry, and any perceived structure would collapse into noise upon close inspection. What appears instead is a consistent pattern, because Atlas carries within its raw signal a directional imbalance that contour mapping merely exposes rather than invents. This principle can be compared to a topographic map, where elevation lines do not generate mountains, but describe slopes that already exist beneath the surface. Atlas therefore does not gain new features through enhancement, but reveals hidden contours that were always present in the measured light field. One of the most important safeguards in this method lies in its reversibility, because enhanced images of Atlas can always be cross-referenced with the raw frames from which they were derived. When both representations display matching geometry orientation and relative scale, the probability of processing-induced illusion drops sharply. In the case of Atlas, the enhanced contours align precisely with faint asymmetries visible in the raw frames, forming a coherent visual narrative across independent treatments of the same data. Atlas therefore satisfies one of the core validation criteria in observational astronomy, which requires that structure persist regardless of how the data is rendered. This persistence matters because contour enhancement amplifies both signal and error, and artifacts tend to reveal themselves by inconsistency rather than repetition. Atlas shows no such inconsistency, as the same sunward-oriented structure emerges whether the data is viewed plainly or mathematically emphasized. The role of contour enhancement here is not to persuade but to clarify, allowing researchers to interrogate the geometry surrounding Atlas without obscuring its original signal. Atlas remains anchored to its photon history, and the enhancement process merely sharpens the questions that the raw data already began to ask. With this principle established, the discussion naturally moves beyond how the structure is seen around Atlas and toward why such structure exists at all, in a regime where disorder should dominate. When geometry is examined alongside light gradients, the question surrounding Atlas becomes less about interpretation and more about alignment, because shapes that repeat across methods tend to reveal an underlying order. Atlas does not present itself as a random scattering of brightness, but as a system where spatial relationships persist, even as visualization techniques change. The comparison begins by overlaying the raw intensity field of Atlas with its corresponding gradient map, allowing researchers to test whether the same spatial biases appear under different analytical lenses. Atlas responds to this comparison with consistency, because the regions of increased brightness in the raw frames correspond directly to zones of steep gradient in the enhanced representation. This correspondence is not trivial, as random noise would generate gradients that shift unpredictably from frame to frame. Atlas instead maintains a stable geometric orientation, with the brightest gradients aligning along a single axis that points inward toward the sun. Such alignment introduces an anomaly, because cometary light distributions are typically governed by outward expansion and solar pressure, which tend to erase directional coherence rather than preserve it. Atlas resists this expectation, showing a gradient structure that appears organized rather than dissipative, even though the object occupies a region where solar influence is steadily weakening. The geometry itself reinforces this departure, because the contours surrounding Atlas do not form concentric shells, but instead stretch asymmetrically, suggesting preferential emission rather than isotropic release. Atlas therefore behaves less like a cloud diffusing into space, and more like a system maintaining orientation against an external gradient. When successive frames are compared, the gradients around Atlas do not rotate, blur, or dissolve into background variation, but remain anchored to the same spatial relationship relative to the nucleus. Atlas thus demonstrates temporal stability, a property that further separates structured signal from transient fluctuation. This stability creates a bridge between observation and inference, because repeated geometry implies a governing mechanism rather than a momentary coincidence. Atlas quietly accumulates weight as an object of interest, not through dramatic change, but through steady refusal to lose form. There is a subtle emotional shift that follows this realization, as certainty replaces dismissal, and curiosity replaces doubt. Atlas no longer feels like an optical curiosity, but like a presence that occupies its data, deliberately holding shape where shape should be fading. The comparison of geometry and light gradient does not explain what at last is doing, but it establishes that at last is doing something consistently. At last invites the mind to slow down, to observe without urgency, and to accept that some structures persist, not because they are forced to, but because their internal rules allow them to remain. From this quiet confirmation, attention begins to move outward away from how the light of at last is arranged, and toward the physical conditions that should have dissolved such order long ago. The confirmation of a physical structure around at last does not emerge from a single image or a single method, but from convergence, because independent paths of verification arrive at the same spatial conclusion. At last occupies a region of analysis, where coincidence becomes statistically unlikely, as repeated observations reinforce the same directional feature. Multiple observatories operating under different atmospheric conditions and using different optical systems recorded the same asymmetric distribution of light around Atlas during the same observational window. Atlas therefore passes one of the strongest tests available in observational astronomy, which is reproducibility across independent instruments. If the structure associated with Atlas were an artifact of a specific telescope detector or optical configuration, its geometry would vary with equipment and observing site. Atlas instead preserves orientation and proportion, regardless of whether the data originates from large professional observatories or smaller amateur systems. This cross-confirmation removes entire classes of explanation, including internal reflections, sensor defects, tracking irregularities, and software-induced distortions. Atlas remains consistent even when those variables are changed, which anchors the structure to the object itself rather than to the tools used to observe it. Temporal persistence further strengthens this conclusion because the structure surrounding at last appears night after night without collapsing into noise or drifting into a new configuration. Atlas shows no sign of transient behavior that would suggest a momentary outburst or a fleeting plume of material. The physical implication of this persistence is subtle but profound, because material distributed in space without governing structure tends to diffuse rapidly under solar radiation and particle flow. Atlas resists that diffusion, maintaining a coherent inner coma whose geometry remains fixed relative to the nucleus. This behavior marks a transition point in the analysis, where Atlas can no longer be treated as a passive reflector of sunlight, but must be considered an active system with internal constraints. Atlas does not merely scatter photons, but organizes them in a pattern that survives scrutiny across scale, method, and time. There is an emotional quiet that accompanies this realization, not excitement or alarm, but a slow recognition that a boundary has been crossed. Atlas is no longer a candidate for dismissal, but a confirmed physical phenomenon demanding explanation. The structure has now been established as real, measurable, and persistent, and this confirmation closes the first phase of inquiry. Atlas stands at the threshold between observation and interpretation, having proven that something is present before asking what that something might be. With the physical reality of the structure secured, the analysis naturally prepares to move forward, shifting focus from whether at last exhibits organized behavior to how such behavior can exist under the thermal and energetic constraints of its environment. At a distance of approximately 2 astronomical units from the Sun, the environment surrounding Atlas changes in ways that are both predictable and unforgiving, because solar energy diminishes rapidly as space expands outward. Atlas receives only a quarter of the solar radiation experienced at Earth's orbit, and this reduction defines the thermal boundary within which most cometary activity begins to weaken. In classical comet models, activity at this distance becomes sporadic and diffuse as the surface cools and volatile materials retreat beneath insulating layers of dust. Atlas would therefore be expected to show a fading coma, one that loosens its structure and gradually blends into the background of interplanetary space. The persistence of organized emission around at last at 2 astronomical units introduces a quiet contradiction, because order typically gives way to dispersion when energy input falls below critical thresholds. Atlas does not conform to that expectation, instead maintaining a defined inner coma whose geometry suggests continued regulation rather than decay. This discrepancy invites a careful reassessment of energy flow, because the Sun remains the dominant external driver of cometary behavior even at reduced intensity. Atlas exists in a region where solar photons arrive less frequently, and with diminished force, reducing the efficiency of surface heating and subsequent sublimation. Water ice, which dominates the composition of many comets, sublimates weakly at this distance, producing slow and uneven outgassing that rarely sustains coherent structure. Atlas nevertheless displays activity that appears controlled, as though the material release is being moderated rather than exhausted. The geometry of this activity matters because isotropic sublimation tends to erase directional features as gas expands freely into surrounding space. Atlas instead preserves orientation, implying that the release of material may be confined to specific regions or governed by internal pathways. This observation does not immediately violate known physics, but it presses against the outer limits of what standard thermal models comfortably allow. Atlas seems to occupy a transitional regime where familiar rules still apply but no longer dominate behavior completely. There is a subtle emotional shift that accompanies this realization, as certainty gives way to attentiveness rather than alarm. Atlas does not demand a dramatic explanation. At this stage, only patience and restraint as assumptions are gently tested. The question is no longer whether Atlas can remain active at 2 astronomical units, but how such activity retains coherence when most comparable objects surrender their form. Atlas invites the observer to linger in this uncertainty, to acknowledge that distance alone does not always dictate simplicity. From this quiet tension between expectation and observation, the analysis begins to drift toward composition, where different materials respond to cold and sunlight in subtly different ways. Water ice defines the baseline of cometary behavior because it is both abundant and predictable in the way it responds to solar heating, and this predictability forms the foundation of most thermal models. Atlas therefore enters analysis through the lens of water sublimation, which weakens rapidly as distance from the Sun increases. At 2 astronomical units, the surface temperature of a typical comet drops to levels where water ice sublimates slowly and inefficiently, producing gas at rates that rarely sustain dense or organized comae. Atlas should, under these conditions, exhibit a thinning envelope of material that expands outward and loses definition with time. The physics governing this process is well understood, as sublimation depends on vapor pressure, surface temperature and exposure, all of which decline as solar flux diminishes. Atlas exists in a regime where water-driven activity is expected to become patchy, localized and ultimately overwhelmed by thermal equilibrium with surrounding space. In practice, comets dominated by water ice show a rapid transition, after perihelion shifting from energetic release to gradual dormancy within a relatively short orbital span. Atlas instead appears reluctant to follow this familiar trajectory, maintaining activity that suggests more than residual water sublimation alone. This does not imply that water ice plays no role in the behavior of Atlas, but rather that its contribution may be insufficient to account for the observed persistence and structure. Atlas challenges the assumption that water sublimation must be the primary driver at this distance, prompting a reconsideration of relative influences. One possible explanation is that the surface of Atlas possesses unusual thermal properties, such as low conductivity or layered insulation, which could delay cooling and prolong sublimation. Atlas could also host subsurface reservoirs that release vapor, more gradually smoothing the decline in activity beyond what surface ice alone would produce. Even these adjustments, however, struggle to explain coherence, because slow water sublimation tends to generate diffuse clouds rather than sustained directional features. Atlas continues to display organization where randomness should dominate, pressing against the limits of water-based explanations. This realization does not close the door on conventional physics, but it narrows the field of plausible mechanisms. Atlas gently redirects attention toward other volatile components, whose lower sublimation thresholds allow activity to persist where water ice falls silent. As the role of water ice reaches its explanatory boundary, the analysis begins to lean towards substances that awaken in colder light, setting the stage for a deeper exploration of composition. Carbon monoxide and carbon dioxide occupy a special place in cometary physics because these volatiles respond to solar energy at much lower temperatures than water ice, and therefore remain active farther from the Sun. Atlas naturally draws attention to these substances as their sublimation thresholds align more comfortably with the thermal environment present at 2 astronomical units. In many comets, CO and CO2 act as early drivers of activity, awakening well before water ice becomes efficient and sustaining faint comae at large heliocentric distances. Atlas could in principle rely on these volatiles to maintain gas production, after perihelion extending its visible presence beyond the limits imposed by water sublimation alone. However, the behaviour typically associated with CO and CO2 differs markedly from what is observed around Atlas because emission driven by these compounds tends to be diffuse and weakly organised. Atlas instead exhibits a structure that appears constrained and directional, suggesting a level of regulation not commonly produced by low-temperature volatiles. The reason for this lies in the physical nature of CO and CO2 sublimation, which usually occurs across broad surface regions rather than through narrowly confined vents. Atlas would therefore be expected to release these gases in a manner that smooths spatial differences rather than amplifies them into coherent geometry. Observations of other comets dominated by CO-driven activity show expanding envelopes that lack persistent orientation as gas escapes freely into surrounding space. Atlas does not follow this pattern, because the structure detected within its coma retains a consistent alignment relative to the Sun over extended periods. This discrepancy introduces an anomaly within an otherwise plausible explanation, as CO and CO2 can account for persistence, but struggle to explain stability. Atlas seems to combine endurance with organisation, a pairing that places additional constraints on any purely compositional model. One possibility is that CO and CO2 within Atlas are not evenly distributed, but instead confined to specific internal pathways that channel release along preferred directions. Atlas could possess fractures or layered boundaries that focus volatile escape, transforming what would normally be diffuse emission into structured output. Even this scenario, however, raises further questions because such pathways would need to remain active and aligned over time despite changes in orientation and solar geometry. Atlas would have to sustain internal coherence in a dynamic environment, preserving direction where turbulence is expected. The role of CO and CO2 therefore remains suggestive rather than sufficient, offering partial alignment with observed persistence, but leaving geometric behaviour unresolved. Atlas continues to resist complete explanation, as each viable mechanism explains one aspect while leaving another exposed. This tension does not invalidate the role of volatile chemistry, but it reframes it as a component rather than a solution. Atlas quietly guides the analysis toward deeper considerations of internal structure and energy regulation, where chemistry alone may not tell the full story. The question of an internal energy source emerges not as speculation, but as a necessity because external solar input alone appears insufficient to explain the sustained behaviour observed around Atlas. Atlas continues to exhibit organised activity at a distance where most objects of similar composition begin to fade into thermal equilibrium. Stored heat from perihelion passage is often invoked as a residual driver, because a nucleus warmed during close solar approach can release energy slowly as it cools. Atlas could in principle retain heat within its interior layers, delaying the decline of activity beyond what surface conditions would predict. However, thermal diffusion is an efficient equalizer, and heat stored in porous ice and rock tends to dissipate steadily, rather than support prolonged regulation. Atlas would therefore be expected to show a gradual loss of coherence if residual heating were the only factor at play. The observed behaviour suggests something more controlled, as the decline in brightness follows a smooth and measured trajectory rather than a rapid decay. Atlas does not display the erratic fluctuations typical of exhausted energy reserves, but instead releases material in a manner that appears paced. This pacing raises the possibility that Atlas possesses internal structures capable of modulating energy release, such as layered compositions or insulating boundaries that compartmentalize heat. Atlas may host regions where thermal conductivity is unusually low, allowing certain zones to remain active while others cool more rapidly. Another consideration involves phase transitions beyond simple sublimation, because some materials can absorb and release energy through structural changes rather than direct vaporization. Atlas could in theory undergo internal rearrangements that liberate energy without immediate dependence on external radiation. These possibilities remain speculative, but they do not violate known physical principles, as they rely on properties observed in other icy bodies under specific conditions. Atlas simply appears to push these properties toward their upper limits, combining endurance with directional stability. The idea of internal energy regulation does not imply an engine or a deliberate mechanism, but rather a system where geometry and composition interact to shape output. Atlas may behave less like a passive object and more like a constrained environment, where pathways and reservoirs govern how energy escapes. Such a model aligns with the observed consistency of the structure, because regulated release tends to preserve orientation rather than dissolve into randomness. Atlas therefore occupies a conceptual space between exhaustion and renewal, where activity persists without obvious replenishment. Emotionally, this realization produces a quiet unease rather than excitement, because it suggests that familiar categories are insufficient without being entirely wrong. Atlas does not break the laws of physics, but it asks them to work harder. The suspicion of an internal energy source remains provisional, framed not as a conclusion but as a working hypothesis, shaped by constraint rather than imagination. At last invites restraint, encouraging the observer to accept uncertainty, while maintaining commitment to measurable cause. This line of inquiry does not yet explain how Atlas maintains direction, but it establishes that energy alone cannot be dismissed as a simple remnant of past proximity. Atlas continues to move outward, carrying with it a question that lingers not because it is dramatic, but because it refuses to fade. The elimination of tracking error begins with motion, because any object moving rapidly across the sky imposes strict demands on observational precision. Atlas reached its closest approach to Earth during mid-December, and during that interval the apparent velocity of Atlas against the background stars increased dramatically. Atlas was not drifting slowly through a static field, but sweeping across the sky at a rate that magnifies even minor imperfections in telescope tracking. Atlas therefore provided a natural stress test for every mount motor and guiding system involved in its observation. In astrophotography, tracking error leaves a signature that is both predictable and unforgiving. If a telescope fails to follow the motion of Atlas accurately, the image of Atlas itself will smear, elongate, or lose its central definition. During the closest approach, observers recorded frames in which the background stars appeared as elongated streaks rather than points. Atlas, by contrast, remained sharply defined at the centre of each exposure. This relationship matters because it reveals which object the telescope was tracking. Atlas was held stationary in the frame, while the stars drifted, confirming that the tracking system was locked to the motion of Atlas rather than to the fixed celestial background. If tracking had been imperfect, both Atlas and the stars would show distortion, or the elongation would align with the direction of the object's motion. Atlas shows no such distortion, preserving a compact core and coherent inner coma across multiple frames. The consistency of this result across independent observations further reduces ambiguity. Atlas was tracked successfully by different observers using different mounts and guiding techniques, yet the outcome remained the same. This convergence eliminates an entire class of explanations that rely on mechanical failure or calibration drift. Atlas cannot attribute its asymmetry to motion blur or guiding instability, when the very conditions that would exaggerate such errors instead demonstrate control. There is a quiet clarity in this elimination, because it replaces suspicion with confidence rather than drama. Atlas emerges from this test not as a victim of observational limitation, but as a source of genuine structure. The emotional shift here is subtle, but important, as doubt gives way to attentiveness rather than surprise. Atlas no longer occupies the category of potential illusion, but enters the domain of physical behaviour that must be explained rather than dismissed. With tracking error set aside, the analysis clears a path toward more demanding questions. Atlas now stands exposed to interpretation, having proven that what is seen follows the object itself, and not the machinery used to observe it. The Prigi passage of December 19th marked a pivotal observational window because proximity amplifies both signal and scrutiny. Atlas approached Earth more closely on that date than at any other point in its trajectory, offering observers a rare opportunity to examine structure with enhanced resolution. At this distance, Atlas appeared brighter and more spatially resolved, yet it also moved across the sky with exceptional apparent speed. Atlas therefore created conditions where any inconsistency in tracking, processing, or atmospheric stability would become immediately visible. Observers responded by adjusting exposure times and tracking strategies to follow the rapid motion of Atlas precisely. Atlas remained centered within the frames, while background stars traced elongated paths that reflected the object's high, angular velocity. This configuration provided a powerful diagnostic because it allowed the separation of intrinsic structure from observational artifact. Atlas preserved a compact nucleus and a defined inner coma showing no elongation in the direction of motion. The clarity of the nucleus region during perigee is particularly important because motion blur tends to erase fine detail first. Atlas retained sharp boundaries even under these demanding conditions, reinforcing the conclusion that the observed asymmetry was not introduced by motion or exposure timing. Frame-by-frame comparison from that night reveals another subtle consistency. Atlas maintains the same relative orientation of its inner structure across successive exposures despite the rapid change in viewing geometry as Earth rotated beneath the observing sites. If the structure associated with Atlas were transient or noise-driven, it would fluctuate or dissolve under such conditions. Atlas instead demonstrates stability holding form as both the object and the observer move. The perigee data also allow for temporal analysis because the object was monitored continuously over several hours. Atlas does not exhibit sudden brightening fragmentation or chaotic expansion during this interval, which further rules out impulsive events. The absence of such behavior matters because close approaches often trigger detectable responses in fragile bodies. Atlas passes through perigee without disruption, suggesting structural integrity rather than imminent disintegration. Emotionally, this phase of observation carries a sense of calm precision rather than spectacle. Atlas does not announce itself through violence or instability, but through quiet persistence under pressure. The perigee analysis therefore serves as a confirmation point, strengthening the case that the structure seen around Atlas is neither accidental nor temporary. Atlas emerges from its closest encounter with Earth unchanged in character, carrying its unresolved geometry forward into the next phase of investigation. One of the most striking properties revealed by extended observation is not the presence of structure itself, but the way that structure refuses to change orientation. Atlas displays an inner feature that remains aligned in a consistent direction, even as the object moves relative to both the Sun and the observer. In typical cometary behavior, directed features such as jets are expected to evolve as the nucleus rotates. Atlas, however, shows no obvious rotational sweep in its dominant structure, creating the impression that the emission is locked in place rather than carried around by spin. This absence of rotational modulation is not subtle, because even slow rotators tend to reveal changes in orientation when monitored over multiple nights. Atlas instead maintains the same geometric relationship between its nucleus and the surrounding structure, as though governed by a fixed internal axis. The persistence of this alignment challenges conventional expectations, because natural outgassing processes are usually sensitive to changing illumination and rotation. Atlas appears to decouple emission geometry from rotational dynamics, a condition that is uncommon, but not entirely without precedent. One possibility is that Atlas rotates extremely slowly, with a period long enough that no measurable change occurs within the observational window. Atlas could therefore present a static face to space, allowing a single active region to dominate emission without noticeable drift. Another possibility involves symmetry within the internal structure of Atlas, where opposing forces or channels balance rotation-driven variation. Atlas might contain aligned pathways that constrain material flow along a stable direction regardless of spin. Both scenarios stretch existing models but remain within physical plausibility, as long rotation periods and internal heterogeneity have been observed in other small bodies. Atlas simply appears to amplify these characteristics, pushing them into a regime where they become visually prominent. The concept of a locked structure carries emotional weight not because it implies intent, but because it suggests constraint. Atlas feels less like a surface responding passively to sunlight, and more like a system expressing its internal architecture through persistent form. This perception alters how the object is mentally framed, shifting attention from external forcing to internal configuration. Atlas becomes a study in stability rather than reaction, in continuity rather than response. Importantly, the locked orientation does not imply rigidity, as subtle variations in brightness still occur. Atlas remains active, but its activity unfolds within boundaries that appear remarkably consistent. Such behavior invites patience rather than alarm, because it rewards long observation over quick interpretation. Atlas does not demand explanation through novelty, but through careful extension of known principles to their edges. As the structure continues to hold its direction, the analysis reaches a quiet inflection point. Atlas has demonstrated not only that it is active, but that its activity is governed by rules that remain to be fully understood. The hypothesis of an anomalous rotation period arises not as an exotic proposal, but as a conservative attempt to reconcile persistence with known physical behavior. Atlas may rotate far more slowly than typical cometary nuclei, and such slow rotation would naturally suppress the visible modulation of surface-driven activity. In most observed comets, rotation periods range from a few hours to a few days, and this rotation exposes different surface regions to solar illumination. Atlas, if rotating on a timescale of weeks or longer, would present nearly the same orientation throughout extended observation windows. This scenario offers a simple explanation for the locked geometry, because a single active region could dominate emission without being carried around the nucleus. Atlas would therefore appear stable, not because emission is constrained artificially, but because rotation fails to introduce variation. Slow rotation is not unprecedented among small bodies, as some asteroids and cometary fragments exhibit periods long enough to challenge detection. Atlas could belong to this rare subset where angular momentum was lost through past outgassing or tidal interaction before entering the inner solar system. However, the slow rotation hypothesis introduces its own constraints because extreme rotational inertia must be balanced against structural integrity. Atlas would need to maintain cohesion while sustaining localized activity over time, without fragmenting or reshaping its surface significantly. Thermal gradients also complicate this picture because even slow rotators experience uneven heating that can gradually alter emission patterns. Atlas nevertheless maintains consistency, suggesting that rotation alone may not fully account for the observed behavior. There is also the question of how such a rotation state would persist during solar passage, when torque from asymmetric outgassing often accelerates or destabilizes spin. Atlas appears to pass through perihelion without dramatic rotational change, implying either internal damping or an unusually balanced configuration. Emotionally, this hypothesis produces neither reassurance nor alarm, but a measured curiosity because it relies on familiar physics stretched thin rather than abandoned. Atlas remains within the domain of natural explanation, yet occupies a narrow margin where multiple conditions must align. The value of the anomalous rotation hypothesis lies in its testability, because continued monitoring can reveal subtle changes in orientation over longer timescales. Atlas will either betray slow motion through gradual drift or force reconsideration if stability persists. This hypothesis therefore functions as a bridge rather than a conclusion connecting observed structure to known mechanics, while leaving room for refinement. Atlas continues outward, carrying with it the quiet possibility that time itself may be the missing variable in understanding its behavior. The geometry of the orbit provides an essential frame of reference, because motion through space is never independent of orientation. Atlas follows a trajectory that lies relatively close to the ecliptic plane, the flattened disk defined by Earth's orbit, and shared by most major bodies in the solar system. This alignment is notable because interstellar objects are not bound to the Sun and therefore arrive from a wide range of inclinations. Atlas could have approached from almost any direction, yet its path intersects the solar system in a manner that echoes the architecture of native planetary motion. From a statistical perspective, such alignment is not impossible, but it is less common than highly inclined trajectories. Atlas therefore occupies a geometric position that subtly influences how solar radiation, gravitational forces, and observational perspectives interact. The proximity of Atlas to the ecliptic plane affects how its coma is illuminated, because sunlight strikes the object at angles that remain relatively consistent over time. Atlas does not experience the extreme seasonal illumination shifts that accompany steeply inclined orbits, and this stability may contribute to the persistence of observed structure. Viewing geometry also plays a role because Earth-based observers are embedded within the same orbital plane. Atlas is therefore seen from angles that minimize extreme projection effects, reducing the likelihood that apparent structure arises purely from perspective. When structure around Atlas appears to point sunward under these conditions, the interpretation becomes more constrained. Atlas is not being viewed head-on along the Sun object line but from an offset angle that allows three-dimensional assessment. This geometry limits certain illusions such as foreshortened tails or line-of-sight compression, which can mimic directional features. Atlas retains its orientation despite changing Earth-Sun object angles, reinforcing the sense that the structure is spatially real rather than geometrically accidental. The ecliptic alignment also influences gravitational context because Atlas passes through regions where planetary perturbations are more likely to accumulate. Atlas therefore moves within a dynamic corridor shaped by long-established solar system architecture. Emotionally, this realization adds quiet weight rather than drama. Atlas feels less like an intruder cutting across space and more like a traveler momentarily sharing the solar system's dominant plane. This shared geometry does not explain behaviour, but it narrows uncertainty. Atlas reveals that even objects born elsewhere must eventually negotiate the familiar shapes imposed by gravity and light. With orbital geometry, established attention begins to shift from where Atlas travels to what external environments it encounters along the way. External influences form the background against which the behaviour of Atlas must be interpreted, because no object moves through the solar system in isolation. Atlas travels immersed in a complex environment shaped by solar radiation, the solar wind magnetic fields and the diffuse material of interplanetary space. The Sun remains the dominant external force acting on Atlas, even at a distance of 2 astronomical units, because its photons and charge particles continue to interact with exposed material. Atlas receives a reduced but steady flux of solar energy, sufficient to drive slow physical processes without producing violent or chaotic responses. The solar wind introduces another layer of interaction. The streams of charged particles flow outward and encounter the expanding coma of Atlas. Atlas would normally respond to this interaction by forming tails that align anti-sunward, shaped by pressure and electromagnetic coupling. What stands out is that the primary structure associated with Atlas does not conform neatly to these expected responses. Atlas displays a feature oriented toward the Sun rather than away from it, suggesting that external forces alone do not dictate its geometry. Solar activity itself varies over time, with sunspots, flares, and coronal mass ejections altering local conditions in the heliosphere. Atlas was observed during a period of moderate solar activity, yet no known mechanism links localized solar magnetic structures directly to stable directional features in a distant cometary coma. This absence of a causal pathway is important because correlation without mechanism does not constitute explanation. Atlas may experience fluctuations in the surrounding plasma environment, but those fluctuations lack the specificity required to impose persistent orientation. The interplanetary medium also contributes a constant background composed of dust gas and charged particles that permeate the solar system. Atlas moves through this medium without exhibiting signs of drag, turbulence, or interaction strong enough to shape its inner structure. Taken together, these external factors establish boundaries rather than answers. Atlas exists within known environmental influences, yet its behaviour exceeds what those influences typically produce. Emotionally, this realization brings a sense of narrowing rather than expansion. Atlas does not invite speculation toward exotic external causes, but instead redirects attention inward. The environment surrounding Atlas appears ordinary, even restrained, and it is precisely this ordinariness that sharpens the question. Atlas continues to express organized behavior without extraordinary external prompting, leaving the source of that order unresolved as it moves onward. The approach of Atlas toward Jupiter introduces a moment of rare clarity, because gravity provides one of the few forces in nature that can be modelled with exceptional precision. Atlas will pass through a region where Jupiter's mass dominates local dynamics, creating a natural experiment that does not rely on interpretation, but on measurement. In classical mechanics, the trajectory of a body encountering Jupiter can be predicted with remarkable accuracy using Newtonian gravity supplemented by relativistic corrections. Atlas therefore enters a regime where expected motion can be calculated in advance, leaving little room for ambiguity once observations are made. The gravitational flyby functions as a scientific anchor, because it transforms speculation into falsifiable prediction. Atlas is expected to follow a specific path, with velocity changes and deflection angles that arise solely from Jupiter's immense gravitational field. If Atlas behaves as a natural object governed only by gravity and minor outgassing forces, then its post-encounter trajectory will align with those calculations. Atlas would emerge from the encounter altered in speed and direction, but not in a way that defies established physics. An anomaly would appear only if the observed path deviates beyond the margin allowed by known non-gravitational effects. Atlas would then exhibit motion that cannot be reconciled with passive response to Jupiter alone.